Picking up where we left off. Again, things are not quite in the right format because I like to have what's in the parentheses, this input, in a different order. First, I like the x to be in the front. So let's just switch those two terms around. So 4 plus 2 f of negative x plus 3. So switch them around, make sure they each keep their own sign. Okay, one more step to do. I need this in a factored form, so that negative needs to be factored out in front of the x. So 4 plus 2 f of, pull out a negative, and then x minus 3. If you distribute that negative through, it gives you this back. And close your parentheses. So we always want our x plus or minus d in the parentheses, and then whatever if there's a factor other than 1 in front of x, it needs to be out front. Once it's in that format, you're ready to list all of your transformations. Now this plus 4 tacked onto the front can be moved to the other end, but either way you're adding to the output, so it really doesn't matter whether you move that one or not. But we make the list of the stuff on the inside first. So minus 3 from the x moves things to the right 3. The negative in front of the x makes the opposite x's. Opposite x's do reflections in the mirror of the y-axis. So a left to right reflection. So that's a reflect in the y-axis. Outside the parentheses controls the vertical changes. So multiplying by 2 does a vertical stretch by a factor of 2. And last but not least, this plus 4 tacked on to the end will move the entire graph up 4. Those three examples are examples where we're using some generic function f of x. We don't really know what that function is, just some random function. On the next page, we get into some more specific examples of functions. So we're going to look at a couple of quadratics and then some other types of functions. The rules are the same. You just have to look for grouping symbols for your input changes. So when I look at this one, I'm trying to find out what has changed from f of x equals x squared, which is the original function, to make it map onto this new graph, g of x, which has some more stuff going on than just an x squared. So the first thing I always look for is the input changes, which would be the things in parentheses with the x. And I notice there's no parentheses around the x, which means there's no horizontal changes that have happened. So the input is untouched. So multiplying by the 5 actually affects the outputs, or the y's. So that does a vertical stretch by a factor of 5. The minus 3 at the end is a vertical shift, so that's going to move things down 3. And then this negative in front we want to deal with separately because negatives do reflections and multiplying by numerical values do stretches and shrinks. This negative is going to take the opposite of the outputs, x squares, which are the y's, flips them top to bottom or bottom to top, so in the y direction, and the x-axis would be the mirror. So that reflects in the x-axis. If I were going to sketch this graph, I would reflect first, stretch next, and move it down last. We always do addition and subtraction last. Order of operations is the boss. 3 more examples. This is another quadratic, so we want to see what's been done to x squared to turn it into this. So before the x gets squared this time, 5 is being added to it. So there is a horizontal change this time. There isn't a number in front of x in those parentheses, which means nothing to factor out. So we can just go ahead and make our list. The plus 5 moves the graph to the left 5 units. The only other change that's happened from x squared is multiply by 2. So the multiply by 2, since it's outside the parentheses, it affects the vertical coordinate, the y coordinates. So that's a vertical stretch by a factor of 2. Two more. This one is just a little bit different because instead of having parentheses, we have a new set of grouping symbols. Grouping symbols come in a lot of different flavors. They can be parentheses, they can be brackets, they can be braces, they can be square roots, cube roots, they can be absolute value bars. Anything that can group terms together is going to act just like parentheses. So in this particular function, we think of this stuff under this cube root, that 3x plus 9, as being in an inner set of parentheses. So this stuff is your input. So I'm going to pretend that that grouping symbol is just a big set of parentheses. The 3 in front of the x is going to need to be factored out of that input. So let's rewrite 4 minus cube root of, factor out of 3, from 3x plus 9, and the other factor would be x plus 3. This 4 on the right end, or sorry, the left end could be moved over to the right end, so I could move that 4 down here and have negative cube root of 3 times the quantity x plus 3 plus 4. That's a positive 4, translates into a plus 4 at the end. Everything inside the root is the input. That means the plus 3 affects the horizontal movement, so that's going to move things to the left 3. The 3 that we're multiplying x by is going to actually multiply the x's by a third in the graph, the reciprocal of 3. So that's going to yield a horizontal shrink by a factor of 1/3. Everything else is outside the grouping symbols, so it's going to affect the y coordinates. So this negative is going to reflect things in the y direction up and down, which is going to use the x-axis as a mirror, while the plus 4 at the end moves the entire graph up 4. Once you learn the set of rules for what transformations are where in the equation, it doesn't really matter what kind of equation you deal with. As long as you can find your grouping symbols, you can separate out your horizontal changes, and anything else outside is going to yield vertical changes. One more on this page, and that's to describe the transformations that map this one, 4 to the x, onto this new one down here. This one's a little bit tricky because 4 to the x is an exponential function, and what students often want to do is when they get down here, they want to consider what the 4 has done, whether it's been a stretch or a shrink, and it doesn't do anything because 4 to the x was already there. So this 4 to the x is the original function's output. It's the things that have been done to it, like minus 7 times 2, and then added, subtracted from 3. Those are actually the changes. Okay, so if I can aim correctly, let's check out all those differences. I don't see any grouping symbols, but I do notice that the exponent has an x minus 7 in it, and since the minus 7 is in the exponent with the x, I can assume that I would subtract 7 from x first if I were doing any operations. So that means that x minus 7 is an understood set of parentheses. Subtracting 7 is being done to the x, not to the output of the function. So that's going to be the same thing as moving to the right 7. And there's nothing to factor out in front of the x, so we don't have to worry about that on this one. The 4 to the x was already there. It's original to the function, so ignore that. Multiplying by 4, we'll do a vertical stretch by a factor of 2. Multiplying that by a negative, we'll do a reflection in the x-axis, and then adding a 3. Notice I didn't move it to the other end, but I could if I want to. I just want to make sure it doesn't look like an exponent if I do. That's a positive 3, so think of it as adding 3 to this business. So that's going to move everything in the function up 3. Oops, we're sliding. Okay, you will need to be able to examine an equation and tell me what's happened verbally like this. You'll also have a handful of problems in your practice problems where I'll give you the list and then you write them in the equation. So you kind of practice doing it backwards. The last piece of the puzzle we actually did on a different day, but I'm going to go ahead and put it in this video because I think I have enough time for at least one of them. And that is how to graph transformations. So I have this graph of y equals x to the third, and x to the third is sort of my parent function, and I want to sketch the graph of the transform function that has these things done to it. So it's been moved left 4, down 3, stretched vertically by a factor of 2, and then reflected in the x-axis. But now the order is important when I draw them. I want to reflect and stretch first, and then shift last, because multiplication gets done before addition and subtraction. So I just need to find some key points on this graph. Like 0, 0 is a great point, -1, -1 is a great point, 1, 1 is a great point. Find some points, move those, and then just sketch in your graph. Okay, so the first thing I want to do is reflect it in the x-axis. So this point is going to reflect up to here. 0, 0 is going to stay put when you do the reflection. 1, 1 reflects down to 1, -1. And then if we re-sketch in our graph, and you can do more points. If you have some other good lattice points in your picture, feel free to use those, and then you get the reflection of it. The second step is to do a dilation twice as tall, 2 times in the vertical direction. So we take each of the key points we had on this first transformation, like -1, 1, and we make it twice as tall, which means we just double the y value, so that goes up to -1, 2. At 0, 0, if you double the y, that's just doubling 0, it's still 0. The point at 1, -1, if you double the y, which is -1, it makes it -2. So it stretches down twice as far from the x-axis. When you reconnect, we'll do a little darker dotted line on this one. It's just a little bit skinnier looking. Last but not least, we needed to move left 4 and down 3. So take each of those points, move them left 4, down 3, move this point left 4, down 3, move this point left 4, down 3, re-sketch your graph, and you're finished. If you do it in stages, it's actually easier than if you try to do all the things in one fell swoop. Let's see if we can squeeze this other one out in a minute and a half. Okay, on this last one, I have to do some rewriting. So if I switch the x's and the 3 around, so -1/2 x plus 3, and then I factor out the -1/2, I need a -6 here because half of 6 is 3. So I'm going to move right 6. I'm going to take the reciprocal of what's in front of the x, so a horizontal stretch by a factor of 2. The negative is going to reflect it over the y-axis, and then move it up 4. Oh, except that I don't have the function to graph. So I guess we're going to not finish this one up tonight, but we would want to do that reflection in the y-axis first, then do the horizontal stretch, and then move it right and up, just like we did the last one. If you do it in phases, just move one key point at a time. If it helps, we even have practiced in class doing the different stages in different colors. So do the reflection in one color, do the stretch in another color, do the shifts in a third color. And we can even do that on the test day. So you might even practice it that way. Almost out of time on this video, so we'll drop here and hopefully be able to figure out what we're doing on the homework.